Listen to this talk on our onboard turbulence recognition system for improved UAS operator situational awareness. The goal of the system is to provide actionable turbulence information to ground-based UAS operators, restoring an important aspect of situational awareness that has been lost in the move from manned to unmanned aircraft. Barron Associates works in areas including guidance, navigation, control, and mission planning, atmospheric sensing and modeling using air vehicles, and human and machine interfaces. We've also worked extensively on verification and validation and assurance of safety-critical algorithms. Notable recent demonstrations of our technologies include testing of both pilot-in-the-loop and fully automated upset recovery capabilities, and a flight demonstration of our turbulence recognition technology using a manned general aviation aircraft as a UAV surrogate. Flight testing of the turbulence recognition technology took place last summer. The need identified by the Navy is to develop an on-aircraft system to recognize and quantify the real-time turbulence levels being experienced by an unmanned aircraft and provide actionable information to a remotely located operator, with MQ-25 as an initial transition target. Key objectives identified by the Navy are to support effective mitigation of turbulence hazards by ground-based operators while minimizing physical changes to the vehicle, to work for a wide variety of aircraft and to account for the characteristics of those aircraft, and to provide outputs that correlate to existing weather products. Operationally, appropriate responses to turbulence are important to maintain safe operations, minimize maintenance requirements, and maximize vehicle lifetimes. Onboard pilots of manned aircraft can of course readily feel turbulence and can effectively assess its severity and take appropriate corrective action, but ground-based operators lack the motion cues the onboard pilots rely on. The goal of this work is to provide an automated system to quantify turbulence and to provide actionable information to operators. Providing this information in a way that relates directly to aviation weather products is one aspect of making it easy to understand, and relating turbulence severity to the limits of the vehicle is another important aspect of the system. This diagram shows key features of the Turbulence Recognition and Decision Support System, which we refer to as the TRADS-UAS system. The system relies only on standard flight control sensors present on nearly all UAS, so no hardware needs to be added. It employs a two-pronged approach to turbulence estimation to support correlation of outputs to existing aviation weather products and to support generation of vehicle-specific warnings, cautions, and advisories. The first component of our two-pronged approach to turbulence quantification is the turbulence energy estimate component, which estimates the energy in the atmosphere in terms of eddy dissipation rate, or EDR, which is the metric most commonly used in aviation weather products. This measure of turbulence is purely a characteristic of the atmospheric conditions and is independent of the type of vehicle. In addition to relating directly to turbulence measures in aviation weather products, this component is well suited to supporting information sharing across heterogeneous fleets. The second prong of our approach is the vehicle impact estimate, which provides a measure of how severely the vehicle is being impacted by turbulence, motivated by turbulence severity category definitions, which relate to altitude, airspeed, and normal acceleration perturbations. The system provides warnings, cautions, and advisories that conform to design standards for the particular vehicle and reflect the operating limits of that vehicle. The development approach includes extensive flight validation with a selection of flight assets motivated by the initial focus on large fixed-wing UAS. The initial flight demonstrations I mentioned previously made use of ground-based LiDAR to provide independent turbulence estimates to validate the system. This slide provides a very high-level overview of the program with an emphasis on demonstrations. We started out with a couple of simulation demonstrations, and as I mentioned, have now completed initial flight validation with a general aviation aircraft as a UAV surrogate. Next up is validation on a business jet to get speeds and altitudes more representative of some turbine-powered UAS, again using a manned aircraft as a UAV surrogate. These manned vehicle demonstrations provide an opportunity to get manual turbulence reports from the flight crew, providing an important validation measure. The final flight demonstration will be in conjunction with flight tests of MQ-25, and we will run on the ground station hardware at the Atlantic test ranges for this demonstration. Key features of our system include the two-pronged turbulence quantification approach that I have already discussed, which provides directly actionable information, as well as facilitating correlation of TRADS-UAS outputs to aviation weather products and supporting sharing across the fleet. By using only existing sensors, we require no hardware changes, have negligible power consumption, and can be deployed on new vehicles at low cost. A ground-based execution option, which will be used in MQ-25 flight tests, eliminates the needs for mods to onboard software, which can further reduce deployment time and cost, while an onboard execution option will support future deployment of the system to support highly automated and autonomous turbulence responses. We hope to transition the technology either directly to the Navy or via a prime contractor, licensing the patent-pending technology and providing technical services to support deployment on new platforms. Key milestones are successful flight demonstrations, including real-time system operation on the 3 previously mentioned platforms, which will culminate with the MQ-25 demo in conjunction with flight tests at the Atlantic test ranges. As previously mentioned, the MQ-25 is our initial transition target. We think our turbulence recognition technology will be particularly valuable for MQ-25 given its aerial refueling mission. Even turbulence levels that are within the operating limits of the vehicle may be undesirable for refueling operations, and the capability to reliably identify such conditions and reposition the MQ-25 into calmer air before the receiver aircraft arrives will offer significant operational benefits. Other Navy transition targets of interest include the RQ-21 and MQ-4. I would also like to note that we are actively developing technology for rotary wing platforms as well. Thank you for listening to this presentation on our turbulence recognition system. Please come visit us at the Sea Airspace Forum. You can stop by our table at the FST booth on Monday or contact me to set up a specific time to talk during the event. Thank you.